Dear students, so in previous class we were discussing about the supremum and the infimum of a set, and we observed that for a finite set the largest element acts as the supremum and the least element is acts as its infimum. Okay. Now let us consider an important lemma. That lemma deals with let U be an upper bound U of a non-empty set. Consider a non-empty set S, non-empty subset so far. Let U be an upper bound. This upper bound U, an upper bound U of a non-empty subset S of R is the supremum of S. Is the supremum of S if and only if for all epsilon is positive, there exists some S epsilon falling S such that U minus epsilon is strictly less than S epsilon. So come to this lemma. If S is a non-empty subset of R, U be an upper bound of this S, then this U become the supremum of S if and only if for all epsilon is positive, there exists an element S epsilon in S such that U minus epsilon strictly less than S epsilon. How to prove this one? The proof is in this way. Let consider S is a non-empty subset of and let U be an supremum or it is an upper bound of S and nothing but it is a supremum of S. Let U be the supremum of S. Means U equals supremum of S. What is epsilon? It is given epsilon is positive. Since epsilon is positive, surely U minus epsilon is strictly less than U. Okay. But what is U? U is the supremum of S. Hence, by the definition of supremum, no number less than U is an upper bound. Since U is a supremum of S and no number less than U is an upper bound of S, so this implies since U minus epsilon is less than U, U minus epsilon is not an upper bound of S. U minus epsilon is not an upper bound of S. Therefore, there exists S epsilon falling S such that U minus epsilon strictly less than S epsilon. Why? Because epsilon is positive, U minus epsilon is strictly less than U, so U minus epsilon is not an upper bound of S, so because U is the supremum of S, hence there exists an S epsilon falling S such that U minus epsilon strictly less than S epsilon. What about the reverse inversion? Reversely suppose that U is an upper bound of S. Let U be an upper bound of S, where S is a non-empty subset of S. S is a non-empty subset of R. Non-empty real subset. Non-empty real subset. Then, it is given there exists some for all epsilon is positive, there exists some S epsilon falling S such that U minus epsilon is strictly less than S epsilon. Now our aim is to show that this U become the supremum of S. So let V less than U. Let V less than U. V presents it. What is U? U is the supremum. Since V less than U, V is in S. So V less than U. That means U minus V should be positive. Okay, U minus V should be greater than 0. Choose epsilon equals, epsilon is a positive quantity, so choose epsilon equals U minus V. Okay. But we have U minus epsilon less than S epsilon. U minus epsilon less than S epsilon means U minus what is epsilon? U minus V. That is strictly less than S epsilon. That implies U minus of U minus V means V strictly less than S epsilon. So V strictly less than S epsilon means V is not an upper bound of S. V is not an upper bound of S. V is known as, what is V? V is chosen in such a way that V less than U. That V is not an upper bound of S means V is an arbitrary element. So this means no element less than U is an upper bound of S. No element less than U is an upper bound of S means what is U? U is supremum of S. So this is what we requires here. So this is the proof of the given lemma. Okay. Now let us consider an important result. Suppose A and B are any two bounded subset of R. A and B are any two bounded subset of R. A and B are bounded. A comma B are bounded. Then A union B is also bounded. A union B is also bounded. This is the first requirement. How to prove this A union B is bounded here? And also we prove that supremum of A union B equals supremum of supremum A supremum B. So first we prove this one. When A and B are bounded, now we have to show that A union B is bounded. For how to prove? Listen. Since A and B are bounded means S it is bounded. If it is bounded above as well as below, means it has both supremum and infimum. Means supremum of A and supremum of B as well as infimum of A and infimum of B are exist. Okay. So let M1 equals supremum of A. Let supremum of A equals M1, comma supremum of B equals M2. Again it is bounded, means it is bounded below, its infimums also exist. So infimum of A equals N1 and let infimum of B equals N2. So these are our assumptions. Okay. Then what is let X fall in A. Let X fall in A. Okay, let X fall in A. Since A has the supremum M1 with the supremum of A means M1 with the least upper bound of A. So by the definition of that upper bound, every element presents in A less than or equals this M1. You can choose X fall in A. This means X less than or equals M1. Okay. Similarly, if X fall in B, then clearly this X less than or equals M2. Why? Because M2 be the supremum of B. Now you can construct or choose M. M equals supremum of this M1 and M2. For the least one, M1 and M2. Since M is the least of this one, means this M1 less than or equals M and M2 also less than or equals M. Okay, M1 less than or equals M and M2 less than or equals M. Why? Because M be the supremum of M1 and M2. Clear? So X fall in A, X less than or equals M1. X less than or equals M1 but M1 less than or equals M. So with the transitive property, X less than or equals M1 and M1 less than or equals M, by using the transitive property, X less than or equals M for all X fall in A. And X less than or equals M2 and M2 less than or equals M, again by transitive property, X less than or equals M for all X fall in B. That means X less than or equals M for all X fall in A union B. That means A union B is bounded above. A union B is bounded above. Okay. Again, infimum of A, now to prove A union B is bounded, it is enough to show that A union B is bounded below. How? That infimum of A is N1. Infimum of A is N1 and infimum of B is N2. Means if X fall in A and N1 be the infimum of A, that means this X greater than or equals N1. For all X fall in A and X greater than or equals N2 for all X fall in B. Why? Because N1 and N2 act as the infimum of A and B respectively. Okay. Now, put a N equals infimum of this N1 and N2. N equals infimum of this N1 and N2 means this N1 greater than or equals N. That means N less than or equals N1 and N less than or equals N2. Okay. So here X greater than or equals N1 and N1 greater than or equals N. So by transitive property X greater than or equals N1 and N1 greater than or equals N, by using transitive property X greater than or equals N for all X fall in A, and similarly X greater than or equals N2 and N2 greater than or equals N, again by transitive property X greater than or equals N for all X fall in B. So that means X greater than or equals N for all X fall in A union B. So that means A union B is bounded below. So A union B is bounded above and which is bounded below, that means A union B is bounded. So when A and B are bounded, then A union B is also bounded. Clear? So this is our first requirement. Agree? Now, so when here we know that when two sets are bounded, then their union is also bounded. When two sets A and B are non-empty subset of S, then if A and B are bounded, then their union is also